Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Someone's coming in. Okay, hopefully you guys are doing well. Let's actually get into it. We started attacking the area problem last time. Which we kind of realized that if we're able to find the area under a curve, it's pretty much just as good as solving the area problem, in the same way that being able to find the slope of a straight line is pretty much equivalent to solving the rate problem. So we developed something called the definite integral, which is going to be a sophisticated approach to actually doing this. And we spoke about the way to do this with a finite approximation, where we do a finite number of rectangles to figure out the area under a curve. And we did the left-hand rule, the right-hand rule, and the midpoint rule. The only difference between these were how we were constructing the rectangles. For the left-hand rule, the left side creates the height of each, the left side of each subinterval creates the height. For the right-hand rule, the right hand of each subinterval creates the height. And for the midpoint, the middle of each subinterval creates the height. The width is a common width called delta x, which we can know its length by b minus a over n by slicing it into an equal number of subintervals, subintervals of equal length, n subintervals. And we looked at how we actually want to do that. What these guys do is they approximate this thing called the definite integral, which is actually just like one of these previous summation of areas of rectangles, which we call Riemann sums. If we let n go off to infinity, we get what's called the exact area, and this is called the definite integral, right? But it is, after all, a limit where you have to compute a limit of things that look like this, f of x I times delta x. Where did I put it? Yeah, you have to compute a limit that looks like a summation of things like that, right? Which can get very hairy, so we're not going to do it. We're not going to do the first principles here. We're just going to skip that. But we did the left-hand rule, the right-hand rule, and the midpoint rule. The steps for each were very similar. You find delta x for the first as the first step. You draw your interval and pick, create the numbers and pick the points that you want. Here we pick all the guys on the left. You set up the Riemann sum and then you evaluate the sum. Right? That was the basic idea. And this is just an approximation for the area under the curve f of x on the interval that you just split up here. Right? For the right-hand rule, same thing. You find delta x. Set up your interval. This time you choose everyone on the right, and then you plug into the Riemann sum, evaluate it. Midpoints, same thing. Find your delta x, set up your interval. Here, you would first set up the interval as normal. Then you want to find the middle of each interval. You can do this by finding the average of the numbers at the endpoints for the first interval, and then repeatedly add delta x after that. And then you can plug that in and get an approximation. And in this case, we saw that this was what was going on, where the left-hand rule gave an underestimate, the right-hand rule gave an overestimate, and the midpoint rule kind of tried to temper in between them. We'll probably see, will we see this by the end of today? Like how to actually get the exact area under this curve and then actually compare it to all these, see which one of these numbers was actually the closest, okay? So to get to that, to find out how to actually compute the exact area, we have to go into another section where we're going to talk about antiderivatives and the fundamental theorem of calculus. So that is where our journey begins today. This brings us into section 5.2. And we begin our discussion with the notion of something called an antiderivative. So the antiderivative of a function is basically the reverse of the derivative, you might think of it. So if you think of the function you have as the result of a differentiation, and you want to figure out what the original function was that you differentiated to get the function that you have now, you say you're looking for the antiderivative. That's how you call it. So the antiderivative of a function little f of x is just another function big F of x, such that if we take the derivative of big F, we get the little f. So if we have a function little f of x, and we want to find a function that I had to differentiate to get that, the function I'm looking for is called the antiderivative. Okay, so as an example, what would be the antiderivative of x squared? So I have a function x squared, and I'm looking for another function that I would have to differentiate in order to get x squared, right? That's the idea. But now x squared is a polynomial. It's a power function, in fact. So I know that a derivative on some other function would use likely the power rule. So then knowing how the power rule works, I would just have to kind of reverse engineer it. So I know that in the power rule, you're going to take the old power, put it down in front, and then subtract 1 from the power, which means the power should be 1 more than what I currently see. So I now see x squared. What this meant was the power was originally 3. So that when the power rule was applied, it reduced it by 1 to get the 2, right? So I know that it should start out with an x cubed. Okay, but then there's something else. Now, if I were to differentiate the x cubed, the 3 would come down and multiply, right? Now the 3 represents 1 more than the power that I currently have, and it's being multiplied. So what I would want to do is I would want to divide by that power. So what I can do here is put a 1/3. And now if I differentiate this function, the 3 is going to come down, cancel the 1/3, and then I'm going to subtract 1 from the 3 to get a 2. So this gives me x squared as the result. So this is an antiderivative, right? So when I said find an antiderivative f of x, what I'm saying is, in other words, what is a function big F so that if I were to take the derivative of the big F, I would get the little f. Which is x squared here. Okay. Now this guy does work. This is an antiderivative of x squared. And how do I know it's an antiderivative of x squared? Since if I were to differentiate this guy, the result would be 1/3 times 3x to the 2, which is x squared. So that is an antiderivative of x squared. Now, it's not, let me in some space here. So remember, as I mentioned before, language is important, how we call things are important. So it should not escape your attention that I just call this an antiderivative as opposed to the antiderivative. So what that means is probably it's not unique. There's probably some other function out there that could work as the antiderivative of x squared. And what would such a function look like? So that might be a follow-up question. Can other antiderivatives be found? And the answer is yes. What else could possibly be the antiderivative of this guy? Well, we also know from derivatives that the derivative of a constant is 0. So that sort of tells you if there was a constant in the original function, it would completely disappear without a trace. So for example, if I said a third x cubed plus 5, this is also an antiderivative. And it's a completely different function. Since if I were to take the derivative of that, 1/3 x cubed plus 5, the result would be x squared. Again, same thing with if I had a third x cubed plus pi. Same thing. Another. Since if I were to take the derivative of a third x cubed plus pi, the result is x squared. This kind of tells you that these antiderivative guys, they're not unique. You can actually have several of them. In fact, for any given function, you would have infinitely many antiderivatives. Generally, we can say big f of x equals 1/3 x cubed plus c is an antiderivative. Okay, now that guy, now that guy is what we call, we give it a special name. This guy here, come on, iPad. It's called a general antiderivative. Because it tells you what the form of the antiderivative would look like in general. And also here, the specific part, namely 1/3 x cubed, is called the primitive, and the c is called the arbitrary constant. It's called the arbitrary constant of integration, which we'll get to. Right? So it's arbitrary because really any constant could actually work here because the derivative of any constant is going to be 0. So the constant is arbitrary. You won't know what the constant is, or if there was even a non-zero constant in the beginning, without more information being given to you. So you'd have to know actually more information about the function to determine what this constant is. So for the most part, we just put a plus c as a placeholder when we're talking about antiderivatives, right? Right. So as the above illustrate, the antiderivative is not unique, and we can talk about it in general terms in this way: big f of x plus c, right? So where I told you there, c is called the arbitrary constant of integration, blah, 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 and f is the primitive. Okay. So for example, I can say the general antiderivative of x squared is x cubed over 3 plus c. Okay, so we're good there. Not sure why this plus c has, looks like there's a lot of space here. Whatever, not going to change this on yet, but that's going to mess things up. All right, so All right. So now we're going to introduce some notation. All the other notes here, I actually already said it, so you can talk about that. As for where the word integration comes from. Right. Integration is the process of finding an antiderivative. Okay. So an antiderivative is the function who, when you differentiate it, you get the function that you're looking at. But the process of finding this function is called integration. We're going to see why it's called integration a little bit later. But now let's actually do a notation check. The general antiderivative of a function f of x is denoted by the following. Now this is a symbol that we saw last time. Notice here that I have that same symbol, but I don't have the numbers on it. There's no a and b. It's just the integral sign that we saw last time without the numbers on it. Right? Last time we saw something called a definite integral. And you'll notice that there was an a and a b on that. There was a number a at the bottom of the s sign, and there was a number b at the top of the s sign. The s sign is called integral sign. It's actually an s because it stands for sum. We're adding up a sum of rectangles. But it had numbers on it. And this was called the definite integral. It gave us a definite answer. Here, we don't have the numbers on it, and it doesn't really give us a definite answer. It actually gives us an answer where it comes with an arbitrary constant, right? And so this here is actually given a similar name. This is called the indefinite integral of f of x. You could say with respect to x, but for nodding top 3, that's not going to matter too much. In other words, this statement is basically saying what is the antiderivative of f of x with the arbitrary constant, right? And it's called indefinite because the plus c, you don't really know what it's going to be. So you're not definitely sure what the function is. So it's indefinite. Now, the word indefinite is often dropped, and we just say the integral of f. And so when people usually say the integral of f, they're talking about the general antiderivative. But when people say the definite integral, they'll put in the word definite. Then there's definitely some sort of computation that is implied where we're finding the exact area under a curve between some interval. Okay. So we can say, make the expression here. So similar to how I can say something like the derivative of x squared is 2x, and I can write that down in symbols as d dx x squared equals 2x. In the same way, we can write down antiderivative using these symbols, right? So I can say the integral of f of x dx is blah, this function plus an arbitrary constant. For example, I can say the integral of x squared is x cubed over 3 plus c, right? And that basically says the antiderivative of x squared is blah, as opposed to saying the derivative of x squared is blah, right? And this is equivalent to saying the derivative of x cubed over 3 plus c is x squared, right? So you're kind of saying it backwards. They kind of go backwards like how exponentials and logs go backwards. Okay. Now, some more things about notation. The dx here in the integral, I'm referring to this part here. That is called the differential, and it is always written to the top and to the right. To the top and or the right, right? But it has to be on top of everything or to the right of everything. So for example, if my function is 1 over x squared, I can write this as the integral of 1 over x squared dx. The dx is to the right. Or I can multiply by the dx and put it on top and say the integral of dx over x squared. These are actually the same thing. What I cannot do is put the dx on the left. That is nonsensical. Makes no sense. People are going to wonder, what are you talking about? You cannot put the dx on the left. You also cannot put the dx on the bottom. For Pete's sake, what are you doing, man? That doesn't make any sense to have the dx on the bottom. The dx is always to the top and to the right, right? You would look like you don't know what you're talking about otherwise, right? So these two are okay. These two, very wrong, not okay. What's going on? Do you need to talk to somebody, right? It's going to be like very like, what's going on? Or you woke up in a daze, like what's happening right now? Okay, you worry about people who would write something like this. You're like, I'm concerned with you as a friend, right? This okay, those not okay. All right, cool. Now we can talk about integration formulas, and the idea is that we want to reverse the derivative rules. Okay, so there are a lot of rules that we were given for derivatives, like the power rule for derivatives, and we can reverse that rule. As I mentioned up here, I kind of talked through it, how I was reversing the rule. Well, I know I have to add 1 to the power because the original differentiation would have subtracted 1 from a power, and because I would have multiplied by the original power, now I need to divide by the original power, right? So that entire thought process can be captured in these formulas, right? So I can say here the antiderivative of x to the n is x to the n plus 1 divided by x n plus 1, right? I'm going to add 1 to the power and then divide by the new power, because that reverses the process of multiplying by the old power and subtracting 1 from the old power, right? And of course, this only works if your n is not equal to -1, because you'd be dividing by 0 in that case. This is called the power rule for integration, right? So there's a power rule for differentiation, multiply by the old power, subtract 1. And there's a power rule for integration, add 1 to the power to get the new power, divide by this new power, right? And that just reverses that. When your n is -1, that's what you would have. So this case covered. Now this, I already started writing everything else very thick. Covered here, right? Because x to the -1 power equals 1 over x. So if I know how to find the antiderivative of 1 over x, I will know how to deal with the n equals -1 case, right? And that, of course, is going to have a natural log involved. We know that the derivative of ln x is 1 over x. So it stands to reason that the antiderivative of 1 over x also is ln x. However, I want you to appreciate that the absolute value signs are important here. Okay, so why is there an absolute value sign? Well, when we're looking at differentiating ln x, I know to even work in ln x, the x had to be positive in the first place. So if I'm given the function 1 over x, though, there's no requirement that the x has to be positive. It's allowed to be negative, right? So how would we deal with the negative side of this graph? Well, it turns out that taking the absolute value of the x actually covers this, right? And we saw, I mean, you probably won't remember this, earlier in the semester. And I mentioned that, oh, there's going to come a reason why I'm showing you this later on, but for now, don't worry about it. That if you were to differentiate the ln of absolute value of x, you would get 1 over x, right? And this is because if your x is negative, then the absolute value is going to change to -x. Apply the chain rule, you'll get -1 divided by -x. You'll get the 1 over x again. So this will cover whether your x is negative or positive, which in 1 over x, it can be negative or positive. Okay, so we have that. Obviously, the antiderivative of e to the x is just e to the x plus an arbitrary constant, just in case there was a constant. And so we have that rule. So these are some nice rules that you want to know. Okay. We can also refine the exponential rule by this. And we'll talk about why this is, or I'll show you why this is the case. But for now, just take it at face value. Yeah, so we will see later why this is. But for now, just take it at face value, that the antiderivative of e to the kx, aka the integral of e to the kx, is going to be 1 over k times e to the kx. So the exponential is still easy to deal with if you have a constant times the variable in the power instead of just the variable in the power. Of course, your constant is non-zero here. If the constant were 0, it would just be e to the 0, you get 1, and then you'd use the power rule because 1 is x to the 0. You just apply the previous rule, right? But this can actually help you out with slight modifications to an exponential function. So for example, I know that the antiderivative of e to the 5x is just 1/5 e to the 5x plus c. Or I would know that the antiderivative of e to the minus 7x is minus 1 over 7 e to the minus 7x plus c, right? Or I can know that the antiderivative of e to the minus pi x, that's just minus 1 over pi e to the minus pi x plus c, right? So these are the rules of antiderivatives, and we have to know them just like we know our derivative rules, right? So I do mention here that you need to have these guys memorized. So the same way you kind of know the power rule for differentiation, you know the quotient rule, the product rule, the chain rule, you know all these, you memorized all these rules. Integration actually comes with rules as well. And while integration comes from the fact that you're reversing a derivative rule, you don't want to have to slowly have to do this in your head. Well, how would I reverse this rule? You should just know how to reverse the rule. It's much easier and it's much nicer. It's actually to your benefit to just memorize these guys and move on with it, and don't worry about it. Okay, so moving on. Let's practice using some of these formulas because that's going to be important. Compute the following indefinite integrals. So we looked at the integral of x squared earlier. What would be the integral of x cubed, right? So here, what you would do is, what happened? Here, what you would do is you would notice this is starting to annoy me now. Okay, so we're back. What you would do here is you would notice this looks like the integral of x to the n dx with n equals 3, which is, very importantly, it's not the same as minus 1, right? So this falls under rule number 1 that I gave you up here. And so you just apply rule number 1, right? So this is going to be x to the 3 plus 1 over 3 plus 1 plus c. or it's going to just be, in other words, x to the 4 over 4 plus c, i.e., what we're saying is the antiderivative of x cubed, or the integral of x cubed, is x to the 4th over 4 plus c. Now, in the future, when you get very good at this, it's okay to skip to this step. Okay, you don't have to show me, oh, I'm doing a plus 1. You should know in your head that you're doing a plus 1. So you're adding 1 to the power and dividing by the new power, right? That is the antiderivative of a power function. Now let's make this a little bit stranger. We have here the antiderivative of the square root of x. Like how would we do such a thing? So we know what the rules say. There's no square root in the rules. So there must be a way to finagle this algebraically to look like one of these rules. Maybe I can write it to look like 1 over x or an e to the x or blah, blah, blah. But we all know what the square root of x is, don't we? This, if written without the radical, this is just the same as saying x to the 1/2. And again, power rule applies. Remember, as always, the rules are our templates. We do not do anything unless we can point to a rule that says we're allowed to do that thing. We might have to rearrange things using algebra so that it's clear that we should apply a certain rule versus not, or apply some other rule. But at the end of the day, you need to know the rules and be good enough at algebra to know that if you're not exactly into one of these rules, you can kind of manipulate things to get to that rule. There are times when you can't do that, though, and we'll deal with that in the next section. So yeah, but for now, we can do that. So it still stands that what I'm going to do is I'm going to add 1 to the power, divide by the new power, plus c. Must do the plus c. Maybe I'll put it way up here. Plus c is important. Do not forget it. I will deduct a point if you forget the plus c. Okay. There's no plus c for definite integrals, but for indefinite integrals, there should be a plus c. So we have that. Now, obviously, that's going to be x to the 3/2 divided by 3/2, which dividing by a fraction is the same as multiplying by the reciprocal. So this is 2/3 x to the 3/2 plus c. Right? And you can always check that differentiating this you should be able to check that. In fact, we can do it. If you took the d dx of 2/3 x to the 3/2 plus c, what you would get is you get 2/3. So it's the constant. We have the constant factor rule. Just leave the constant alone, differentiate the function. So 3/2 comes down, and I take 3/2 minus 1 plus 0. These guys are going to cancel, obviously. And so I'd be left with x to the 1/2 plus 0, or the square root of x. Right? So that works. Right? The power rule does reverse that. Now you look at this one. Integral of x plus 1 all over x. You will notice that we do not have a rule for rational functions. So don't even think about that. In fact, there is a very clear and present danger here. Warning. The integral of one function divided by another function is not the same as just integrating the top and then integrating the bottom, right? Why would it be the same? When we have derivatives and we want to differentiate a fraction, there was a whole quotient rule to go through. Obviously, if we're reversing something like that, it's not going to be straightforward, right? So don't do that, which is very common, right? You can't just integrate the top and the bottom, right? So that's the first thing you want to know. Right? It didn't work for derivatives. There's no way it's going to work for antiderivatives. They're reversing the derivative. It's like we're doing a derivative backwards. You think that's going to be easier? No. So here, we know we cannot do that. We should not do that. So what can we do? Well, we have all these rules. The idea, of course, is to rewrite it to look like one of these rules. So now we start thinking about simplifying. So we can simplify rules do not directly apply. So try simplifying. Okay. Now, how do we simplify this? Well, it shouldn't be that bad. You're dividing by x. Just divide x into each thing. So this is really just asking about the antiderivative of this. Now, it turns out that derivatives share very similar properties. Integrals share very similar properties to derivatives. Integrals also obey the constant factor rule. And the sum difference rule. Which I guess later, if I tell you about the properties of integrals, I would actually mention this in a theorem or something. i.e., if I want to find the antiderivative of a constant times a function, it's going to be the same as a constant times the antiderivative of that function. You can factor constants in and out. And if I wanted to find the antiderivative of the sum or difference of two functions, it's actually the same as finding the antiderivative of each thing in the sum and then adding them together. That's true. Okay. So now, this thing, I can kind of think of it as right. So you can think of this as blah, and do one at a time. But again, you don't always write that out. Just like how with derivatives, if you have the derivative of sun, you don't really write out, oh, d dx of this plus d dx of that plus d dx of that. It's just a waste of time. You just know in your head, just do one at a time, right? So now we have the antiderivative of 1, and of course, that's just x. By the power rule, or just know that the derivative of x is 1. And then we have the antiderivative of 1 over x, which is exactly a rule. It's ln of absolute value of x. Say again, absolute values are important. Of course, there's a reason I'm repeating this that often, but we'll see how many people take heed. So yeah, we can do that. And we can go even more complicated. Maybe. Might be complicated if you don't know what to do. But we here have the integral of the square root of x plus 3 over x squared dx. How are we going to do that? I think that's delivery or something. Well, again, it's simple. You rewrite it in terms of doing the rules, right? So we rewrite it so that we can see that, hey, rules would apply here. So this is x to the 1/2 plus 3x to the minus 2. Rewrite it in terms of powers because you have a power rule. Now, here, you would think of this as, well, it's the integral of x to the 1/2 dx plus the integral of 3x to the minus 2 dx, which I just told you about the constant factor rule. So the 3 can just come out, and we do that. And now we just do the power rule. But I'm writing this in blue because I wouldn't expect you to write it out. I don't think it's necessary for you to write it out because with enough practice, you'll just see these things. Kind of like how you got a lot of practice with derivatives. And if I just gave you a list of things, differentiate 5x squared minus 3x to the 7th plus 15x to the 4th, you can just do that all in your head, hopefully by this point. So we just know to do each of these one at a time. So we know that the first one is 2/3 x to the 3/2. Because I have 1 over 2 plus 2 over 2, I get 3 over 2, and I know I'm going to flip it and multiply. Plus, here it's 3 over minus 1 times x to the minus 1, because I add 1 to the power. 1 plus minus 2 is minus 1, divide by minus 1. Don't forget the plus c. Okay, plus c's are important. And so we have here 2/3 x to the 3/2 minus 3x to the minus 1, or you can even do 3 over x if you want. For now, everything else is the same old, same old. The rules I gave you above are all the rules I expect you to know in this class. In the other calculus class, there would be many more, but for now, you just have to remember 3 or 4 of them. You can actually remember rule 4 in place of rule 3, and just think of rule 3 as rule 4 with k equals 1. Just to remind you of what that is. Right, rule 3 is like e to the x, whereas rule 4 is e to the kx. Of course, if I plug in k equals 1, I get rule 4 becomes rule 3, right? So you could memorize 3 rules. What about this one? Well, I know this is going to be equal to 3 to the x minus 7x to the minus 3. Just rewriting it. Of course, in my mind's eye, I would think of this as, oh, this is 3 times the integral of e to the x minus 7 times the integral of x to the minus 3. Right, but I can just write it down like I'm just doing one at a time. The antiderivative of e to the x is e to the x. So that stays as 3e to the x. And then I would have a minus 7 times, add 1 to the power, divide by the new power, plus c. And then I would have, well, 3e to the x plus 7 over 2 x to the minus 2 plus c. Or, of course, 3e to the x plus 7 over 2x squared is another way to write this, plus c. This one, same idea. You realize that this is just 4 times the integral of 1 over x minus a third times the integral of e to the 2x. We know how to do each of these. This is 4 times ln of absolute value of x minus e to the kx is 1 over k e to the kx. This is 1 over 2 e to the 2x. And that's that. Okay. So those are all the computational examples that I wanted to do. Next time, we're going to bring everything full circle, go back to the area problem, and you're going to realize why me showing you these things that I just showed you is actually relevant at all to this discussion. So what we did was just told you how to compute indefinite integrals. But I'm actually going to use an example that we used to motivate the idea of the derivative, that whole thing where the object was moving at constant speed. It covered 150 miles in 3 hours. You might have remembered that. And we actually used that to figure out, hey, the slope is equivalent to how fast it was moving, and we got derivatives. I'm going to start with the same example and kind of show you the motivation for thinking about an antiderivative as a way of getting an area. And we're going to actually connect those two with something called the fundamental theorem of calculus. And you're going to realize that we can use these antiderivative calculations that I've been doing to find areas. And after that, we're going to do integration by substitution and area between curves. So on Tuesday, we're going to do the fundamental theorem of calculus stuff, maybe start substitution. And on Wednesday, I will finish up substitution and talk about applications, which would include area between curves. So I think I'll talk about 3 applications, but I really only expect you to know 1. I'll probably use the other 2 as some sort of bonus material. But yeah, also you may remember I mentioned on Wednesday, we're going to do an asynchronous lecture, and I'm just going to have you do the test over a 24-hour period. So I might record the lecture during the same class time, during the usual class time, so that you guys can join and ask questions if you want, but you don't really have to show up on Wednesday. Just make sure you do your test on Wednesday. Yeah. Yes, James?
So the test it's Wednesday, not Tuesday, then?
Correct.
Okay, and then there's a quiz this Sunday?
There's a quiz Sunday, right?
Okay.
But the quiz only goes up to everything since the last quiz and optimization.
Okay, so no integrals or antiderivatives?
I'll put them in the bonus.
Okay, gotcha.
But your test would cover everything up to what I did today.
Gotcha, thank you.
Right? So I have a regular class on Tuesday where I'll do some more stuff in line with this. And then on Wednesday, it's test day. Take it whenever you want over a 24-hour period. Right? It'll be something like from after class on Wednesday, which is 12:30, 12:20-ish, and then it would continue until 12:20 or 12:30 on the following day. on Thursday. It will still be timed, so you'll still have a short amount of time to do it, but you'll be able to log in and do it anytime over that period. Yeah, I think we can stop there. So that's it. Thank you for your time and attention. I will remind you guys of everything I just said, announcement-wise, in an email or something. But for now, go forth. I also have the notes for the things I will be doing in the notes already, so it's already pre-typed. You can start to read through some stuff, see if you can pick up anything before we actually get to it. But eventually we'll get to it and finish off. That's it. Thank you for your time and attention. Enjoy the rest of your weekend, and I will see you guys in the next one. Ciao.